Okay, guys, this is chapter 9.2, multi-stage experiments and modeling. Okay, so first of all, we want to talk about tree diagrams. That's one way we can model these experiments that was just mentioned. So, for example, here, okay, suppose the spinner is spun twice. The tree diagram shows the possible outcomes. So the reason this is called a tree diagram is because we make these branches for each stage of the experiment, right? So on this one, it's talking about spun twice. So we're going to have two sets of branches, right? And the first set, or first spin, the spinner could land on a blue, a red, or a yellow. So we branch off to those three different things. Notice the probability of each of those events happening, since they're equally likely, right, is each 1/3. Now on the second spin, we still have the same option. We can land on blue, red, or yellow, but if we landed on blue the first time, then the next spin could still be blue, red, or yellow, right? Which would give us two blue spins in a row, a blue spin, then a red spin, a blue spin, then a yellow spin. Same thing if we'd have landed on red first. We still have the same three options. A red one and then a blue, a red one and another red, a red and a yellow, and still 1/3 probabilities. Now notice what that means. Here's my total outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So what's the probability that they're both blue? Oh, 1 out of 9. Notice another way we could get that is by multiplying 1/3 times 1/3 is 1/9. As a matter of fact, that's something called our fundamental counting principle, right? The fundamental counting principle tells us that when we're trying to figure out the number of ways something can happen, we multiply the numbers together. If I have 3 shirts, right, and 4 pair of pants, then I have 12 total outfits, 3 times 4. Okay, and now they're showing you that this is our sample space, right? Because it's every possible outcome. That's what the sample space is. And notice the probability of each outcome is 1/9 because there's 9 of them. And we can get that right here. 1/9, 1/9, 1/9, right, by multiplying. Okay, alternatively, we can generate the sample space using a table. So we could have said blue, yellow, red, and then, I could get one that's a blue, blue, a blue, yellow, a blue, red. About the only place we're going to see this in this course is when we think about rolling a pair of dice. Okay, we've talked several times about, probabilities rolling a single 6-sided die. When you roll a pair of dice, we usually talk about, the sum of the two numbers that's showing. Now, a lot of times people think, oh, there's 6 and 6. That gives me 12 possible outcomes. Remember that fundamental counting principle we just talked about. You would multiply 6 times 6. And we can make a little table to actually show us what they are. Okay, sometimes people are like, well, this is a 3 and a 3. That's not different. Think about if you had 2 different color die, and maybe these were all red, right? And then your other die was a green die, so these were all green. So this is the difference in this row. Okay, so having a red 2 and a 1 green is a different roll than having a red 1 and a green 2. Okay, so that's why these are considered different rows. These are two different rows. Notice here, if I had a red one and a green one, that's the same thing as having a green one and a red one. All right, so we're going to talk about dice quite a bit. So it's going to be important to keep this in mind, that there's 36 possible outcomes, and I need to be able to maybe make this chart or keep this chart accessible to me somewhere, since we now have the luxury of using our notes. Okay, so let's see, here's our question. When rolling a pair of fair dice, find the probability of the event A rolling double sixes. Notice there's only one way here that you can roll double sixes, and there's 36 possible numbers you could get. So the probability of rolling double sixes is 1 out of 36. Find the probability of rolling a sum of 7 or 11. Okay, notice that word or. So here's what we're doing. The probability of rolling a 7 or 11. Remember our formula for or. It's the probability that you roll a 7. And notice how handy this little chart makes it. Look, all of these are the 7s, right? Notice this is your diagonal of 4s. This diagonal is all 5s, etc. So I'm going to find the probability that I roll a 7. 1, 2, 3, 4, 5, 6 different ways that can happen out of 36 possible ways, plus the probability of you rolling an 11, right? There's only 2 ways that can happen, minus the probability that it's a 7 and 11 on the same roll, and that can't happen. These events are mutually exclusive, right? I can't roll a pair of numbers that give me a 7 while at the same time adding to 11. So our probability that we roll a 7 or an 11 is 8 out of 36, or since both of those are divisible by 2, I said by 2. Oh, well, that was right. Both of those are divisible by 4, then I have 2 over 9. Okay, a fair pair of dice is rolled. Let E be the event of rolling a sum that is an even number, and F the event of rolling a sum that is a prime number. Find the probability of rolling a sum that is even or prime. And it shows you the notation there. That is the probability that it's even or a prime. Okay, so this is the probability that your number is even. Now notice what they've done for us here. What's this? Oh, that's E or F from up there. All right, well, I'm going to, instead of doing that, instead of looking at that, let's go back and figure that out for ourselves, right? All right, so we want to say even or prime. Notice what I have here. Notice what my possible rolls are. Okay, you can get numbers that add to give 2, so that's even, right? An even number. Okay, 2. Numbers that add to give 4. Numbers that add to give 6. But don't forget, these numbers all add to give 8. These numbers all add to give 10. And then these numbers add to give 12. So those are my ways that I can get a sum that's even. Okay, my primes, prime numbers are, well, 2's a prime number, 3's a prime number, 5, There's some 7s. 9's not prime, but 11 is. Okay, so if I want to know the probability that the number is even or prime, I've got to figure out the probability that it's even. Now think about this though. There are, let's take the 4 for example. There are 1, 2, 3 ways to get 4. So right here, here's one even number, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 18 rows out of these 36 rows that would give me an even number. All right, and then because we're doing an OR again, I just want to find out how many give me a prime number. All right, and prime numbers are 2, 3, 5. So there's 1, 2, 3. Here's my row of 5s. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 out of the 36 are prime numbers. Now I need to know if any of these numbers are even and prime. Yes, however many ways you can get a 2, and there's only one way you can get a 2, so I need to take that away because I counted that one right here and I counted it again right here. So my final solution is 18 plus 15 minus 1. So let's see, 18 plus 14, 32 out of 36. Okay, which is, they're both divisible by at least 4, so 8/9. Okay, and that's the one we just kind of went back and worked on while we could see our chart. Okay, more multi-stage experiments. So let's look at this box in figure A. It contains 1 colored ball and 2 white balls. I'm just going to call it black instead of colored. If a ball is drawn at random and the color is recorded, then a tree diagram for the experiment might look like this. In other words, because there's 3 balls, right, you would have 3 branches, and each has a, is the same likelihood of being drawn, so each probability is a 1 out of 3 chance of being drawn. But think about this, because these are both white balls, couldn't I just simplify this tree diagram and make this probability 2/3 and this one 1/3? Yeah, I can. Okay, so we're going to keep that in mind. And let's look at this experiment. Suppose a ball is drawn at random from the box in the figure and its color is recorded. The ball is then replaced and a second ball is drawn and its color recorded. The sample space for this 2-stage experiment can be recorded like this. You're either going to get 2 black balls, right? You can get a black ball on your first draw and then a white ball on your first draw and then a black, or they could have both been white. Okay, let me see if they're asking us a question on that. Yeah, okay. All right, so there's my sample space. Now this tree diagram for this experiment is shown below. Okay, so because, let's refresh our memory, the box has 2 white balls and 1 black ball. So on your first draw, it's a 1/3 probability you're going to get a black ball and 2/3 that it's going to be a white ball. I'm going to, just to keep that over here, Here's what our box looks like from before, right? Okay. So let me see if oh, I can't remember it. I just read it, but are we, and then the ball is replaced because that matters. Okay. So, and then the ball is replaced. So we've got the same probabilities each time. So we could draw a ball out. If it's black, there's a 1/3 chance that's happening. If it's white, there's a 2 out of 3 chance that is. We put it back in and we draw again. So it doesn't matter if we drew a black ball or a white ball from the first draw. We still have the chance to get a black or a white ball next time, right? With the same probabilities because we just put our ball back in there and nothing changed. But now I can figure out the probabilities for particular outcomes. What's the probability that you draw 2 black balls, that both of them were black? 1/3 times 1/3, right? That you drew a black ball and then a white ball? 1/3 times 2/3. A white ball and then a black ball? 2/3 times 1/3, and 2 white balls. Now notice, so we're going to do this quite a bit. And notice a check for me is these probabilities I get here, they better add up to be 1. Because remember, our sample space has to account for 100% of the possible outcomes. These all have a denominator of 9. 4, 5, 6, 7, 8, 9. So I feel comfortable that doesn't guarantee I didn't make a math mistake, but I'm always going to do this and double check, right? It needs to always add up to 1, all my different possibilities. And we'll do some examples of this coming up. Okay, for all multi-stage experiments, the probability of the outcome along any path of a tree diagram is equal to the product of all the probabilities along the path. That's what we've already said. We're just multiplying each probability along the path. Suppose 2 balls are drawn, 1 by 1, without replacement. So once again, I think they're talking about that same box. So let's refresh our memory and put that box right here. All right, so the first part of our tree diagram is the same, right? There's a 1/3 chance to draw a black ball and a 2/3 chance that I draw a white ball. But think about this now. If my first draw was the black ball, it now gets removed. And what's left in the box is this, right? So for my second draw, I can't even get a black ball because I've already taken it out. And there's a 2 out of 2 or a 100% chance that that next ball will be white. Okay. So that gets me this stage. If the ball I had drawn on my first draw was white, then one of these would be removed and I would be left with this for my second draw, meaning that there's a 1 out of 2 chance I'm going to get a black ball this time and a 1 out of 2 chance I'd get a white ball. So now here's my possible outcomes. 2 blacks, but notice that would be 1/3 times 0, right? Black first and then white, 1/3 times 1, or 1/3. White and then black, 2/3 times 1/2, or 1/3. And then 2/3 times 1/2, again, 1/3. I'm going to double check my math and see that they all have a denominator of 3. 1, 2, 3. Okay, so once again, I feel kind of comfortable with my problem there. Independent events. Independent is another term we need to know, just like we need to know that mutually exclusive. They're kind of related. Mutually exclusive goes with or events. Independent goes with and events. So I can tell we're about to talk about and probabilities. So independent events are when the outcome of one event has no influence on the outcome of a second event. I think the best example of this is like drawing, say you have a deck of cards and you're talking about the probability of drawing a king and a queen, right, with two draws. Now, if you're just talking about one draw, that probability is 0 because you can't have one card that's a king and a queen on the same card. But here we're talking about two events, two draws. Okay, if you draw one card and you look at it, then you put it back in and you shuffle the deck and draw another one, those events are independent, right? The outcome of one has no effect on the outcome of the other. But if you draw a card out first and then you don't put it back in, then the probability of drawing a queen on that second event has changed. So let's model what that would look like. Okay, so this is saying a probability of drawing a king and a queen, okay? And let's say this is with replacement. That's another thing that tells you that it's independent if you talk about with replacement. Okay, so the probability you draw a king, there's 4 kings out of 52 cards. You put it back in, shuffle them up, so that means there's still 52 cards, and there's 4 queens for you to draw. But if you wanted to figure out the probability without replacement, right, without replacement, the first draw is still the same. There's still 52 cards, and 4 of them are kings. But on that second draw, if you're still holding that king in your hand, there's now only 51 cards, right? Now, there's still 4 of them that's queens at this point. So if you talked about 2 kings, this would change to a 3 now, because there would only be 3 kings left in there. But notice different numbers, different probability. So when we're doing and probabilities, we got to think about, are the events independent? When we're doing or probabilities, we got to think about, are the events mutually exclusive? Okay, if 2 coins are flipped, an event E sub 1 is getting a head on the first coin, and E sub 2 is getting a tail on the second coin, then E sub 1 and E sub 2 are independent events because one event has no influence on possible outcomes. You flip a coin and then you flip it again. It doesn't matter what you got on that first toss. You still have a 1 out of 2 shot of getting a heads or a tails on that second toss. Okay, here apparently they're going to model that for us with a tree diagram. Okay, first flip, 1/2 probability that it's heads, 1/2 that it's tails. Second flip, same thing, right? They're independent, so those probabilities are still 1/2. So then you can go through and multiply 1/2 times 1/2, 1/4, 1/4, 1/4, 1/4. These all add up to 1. So we feel comfortable about that diagram and the probabilities that they got. All right, for any independent events, and again, I don't know why this and never comes through, but this is supposed to be an and. So the probability of your first event and your second event is telling us we just multiply. So here's another formula to add to our list. It's for and probabilities. We just have to be careful, are they independent events? Because this second event, the probability of it could change depending on if they're independent or not. But that's my formula for and events. Add it to your list. Okay, the figure shows a box with 11 letters. Some letters are repeated. Suppose 4 letters are drawn at random from the box, one by one. Without replacement, that's important to know, always, without replacement or with replacement. Either way, it doesn't matter. It's just important to know which one. What's the probability of the outcome baby? What I need to realize about this is that means what's the probability that I draw a B and then an A and then a B and then a Y, right? This is what's important. I have to realize this is an and event, right? Oh, if I want those letters chosen in that order, then it means draw a B out and then draw an A and then draw a B, etc. So once I realize it's an and probability, I just multiply them, right? All the 4 probabilities. The probability you get your first B, well, there's 2 B's out of the 11 letters. It told me up there it was 11, or I could just count the letters. But remember, it's without replacement. So once I've taken that B, one of the B's out of there, the probability I'm going to get an A is 1 out of 10 choices now. Okay, now that I've removed the A, there's 1 B left out of the 9 choices. And now that I've removed it, there's 1 Y left out of the 8 choices. Okay, so I just multiply them all together. 1 out of, let's see what that is. 3,960. Okay. Not going to happen very often that you draw out the letters B-A-B-Y, is it? Possible though, possible. Okay, consider the 3 boxes shown below. A letter is drawn from box 1 and placed in box 2. Then a letter is drawn from box 2 and placed in box 3. Finally, a letter is drawn from box 3. What is the probability that the letter drawn from box 3 is B? And then they're going to call that our event. Okay, I think I made a page here. Yeah, okay. All right, so this is a 3-stage experiment. Okay, so my first stage, I can either get an A or B out of the box. The probability I get an A is 2/3, and the probability that I get a B is 1/3. Now, if I put an A in here, if I drew an A the first time, then on my next draw, there's still choices of A and B. No matter what happened on my first draw, there are still A's and B's in this box. So now, if it looks like this, if I took an A out of here and put it in that box, and then I reach in here and draw, this probability is 2/3, and this probability is 1/3. But if I would have drawn this B, which is what this branch is saying, and put in here, now the probability of drawing an A is 1/3, and the B is 2/3. Okay. The last branch, I still have choices of getting either an A or a B for each draw. Come on now, pen. All right. So, starting with this one, if I would have moved an A into this box, right, And then I reach in that box after putting an A in there. I reach in. There's a 2 out of 5 chance that I'm going to get an A, and a 3 out of 5 chance I'm going to get a B. Since here's another option where I've put the A in, I'm going to go ahead and fill these probabilities in also, so that I just to save time, right? Okay, because this is the same thing. It's just what I did on the first draw doesn't matter. This is still, hey, I've put an A in there, or I've put an A in there. Okay. Or I could have put a B in there, right? Which would be right here. If I took a B from the second box and put it in there, and now I'm going to draw, I would have 1 out of 5 chance of getting an A and a 4 out of 5 chance of getting a B. Same thing down here. 1 out of 5 chance of getting an A, 4 out of 5 chance of getting a B. Now, notice all my outcomes, my possible outcomes are A, A, A. I'm just following each path. And then it's A, B. Right? A, B, A. A, B, B. B, A. B, A, B. BBA, or all three could have been B's. Okay, there's my sample space. Well, technically in this question, it just said, what's the probability your last letter drawn is a B? So really, I'm only looking at this one, this one, this one, this one for my event, but I just listed them all just, again, just for practice of, hey, this is what it tells us, go through the path. And I can find the probability of each one by simply multiplying each path. 2/3 times 2/3 times 2/5. Right? On fractions, you just multiply straight across the numerator, straight across the denominator. So the probability of this one is 8 out of 45. And then if I multiply 2/3, 2/3, 3/5, that's 12 out of 45. And then this path is 2/3, 1/3, 1/5. Is that a 1? Yeah, that's a 1. So 2 out of 45. This one is 2/3, 1/3, 4/5, so 8 out of 45. 1/3, 1/3, 2/5, 2 out of 45. 1/3, 1/3, 3/5. I know I could cancel here, but I want all my denominators the same so I can add them together easy anyhow. So I'm just going to say 3 out of 45. Okay, and then 1/3, 2/3, 1/5, so 2 out of 45. And finally, 8 out of 45 again. Now, every single time, if I were you, I would check this. This better be 45 out of 45. So let's add them together. 20, 30, 35, 45. Perfect. So I feel comfortable. Again, it doesn't really mean I didn't make a mistake, but I certainly feel comfortable. And if I would have gotten something other than 1, I know I've made a mistake and I could go back and check my math. So the original question was just what's the probability you draw a B out of that last box, right? So it's this one, this one, this one, and this one. And I just add those up. So 12 and 8's 23, 31 out of 45. Final answer. All right. That's pretty fun, isn't it? Conditional probabilities. If A and B are events in sample space S, and the probability of A is not equal to 0, then the conditional probability that event B occurs given that A has occurred is given by this formula. So the important part here is given that, and again, this should be an and. So here's another formula you can put on your list. Technically though, on conditional probabilities, I really don't need a special formula for it. Okay, if I'm given some information, some particular information that I already know about my draw, in other words, what's the probability that my card I drew is a heart, given that I know it's a king? Well, if it's a king, the probability it's a heart's 1 out of 4, right? I can fill the information into this formula, but I don't really need this formula. Okay, let's see if this is a, yeah, if you know. So, for example, on this one, what's the probability of rolling a 6 on a fair die if you know that the roll is an even number? Okay, and so here they've explained it to you using the formula. Okay, but think about this. If you know that the roll is an even number, the only ones you're concerned about are 2, 4, and 6, right? Because you know that roll's even. So what's the probability at 6 if you have 3 to choose from? I think that's way easier than following this formula. But there's the formula for you if you so choose. Okay, so now we're just left with some examples. So a box contains 3 white balls and 2 black balls. So let's draw it. Okay, so here's our box. A box contains 3 white balls and 2 black balls. A ball is drawn at random from the box and not replaced. Then a second ball is drawn from the box. Draw a tree diagram for this experiment and find the probability of the event that the 2 balls are of different colors. Okay, so the first draw out of the box, you can get a white ball or a black ball. The probability it's white is 3/5. The probability that it's going to be black is 2/5. Now, it's not replaced. So if you drew a white ball out of the box, your new box looks like this. So on your next draw, you still have a chance of getting a white or a black ball, but your probabilities have changed. Now the probability it's white is 1/2, 2 out of 4. Likewise, black 1/2. Okay. Had you drawn a black ball without replacing it on the first draw, your new box you're reaching into looks like this. So once again, you still have white ball and black ball choices, but your probabilities have changed. The probability you're going to get a white ball now is 3/4, and the probability you're going to get a black ball is 1/4. Okay, so here's your sample space, all your possible outcomes. They could both be white balls. You could have drawn a white ball and then a black ball and then a white ball, or you could have drawn black balls both times. Okay, so our probabilities, you just multiply. So 3 times 1 and 5 times 2. 3/10. 3/5 times 1/2. 3/10. 2/5 times 3/4. 6/20. And here, I might want to simplify that because I'm going to add them together. So let's just go ahead and simplify this, right? The 2 and the 4 can divide out, or I can divide a 2 out of each of these, however you think of it. Whoops. Whoa, we definitely don't want anything looking like that. Okay, and 2/5 times 1/4, so 2/20 or 1/10. Double checking ourselves. Denominator's 10 on all of them, so 3, 6, 9, 10. Perfect. Now, the question is, find the probability that the 2 balls are different color. That's this one and this one, right? So 3/10 plus 3/10, 6/10, or 3/5. The probability you're going to get 2 balls of different colors under those conditions is 3 out of 5. There are 40 employees in a certain firm. We know that 28 of these employees are males. 2 of these males are secretaries, and 10 secretaries are employed by the firm. What is the probability of the event that an employee chosen at random is a secretary? Oh, look, given that the person is a male. I could look at my formula and plug those numbers in based on my formula, or given that the person is a male, all I'm interested in looking at is the 28 males, right? So how many are secretaries out of those 28? 2 of the males are secretaries. What's the probability that it's going to be a secretary given that the person's a male? 1 out of 14. Whoops, I forgot to erase it. I was about to move on without. Okay. A husband and wife discover that there is a 10% probability of their passing on a hereditary disease to any child they have. If they plan to have 3 children and passing on the disease to the children are independent events, so one child having the disease has no bearing on another child having the disease. What's the probability? At least, that should be a 1, I'm sure, at least one child will inherit the disease. Okay, well, if they're going to have 3 kids, right, they can have a child with the disease or a healthy child on the first one. Same with the second one. It doesn't matter if the child had the disease the first time or not. Their second child can still either have the disease or be healthy, no matter what happened with the first child, and the same with the next child. Okay, it says there's a 10% probability passing on the disease. So 10%, that's 0.1, means 90% chance the child will be healthy. These are independent, so they're all the same, right? 10% chance it'll be healthy, 90% chance the child will have the disease. Okay, so this one, all 3 children have the disease. the probability of that happening is 0.1 times 0.1 times 0.1, or 0.001. Here we've got the first two have it, but then they have a healthy third child. Okay, 0.1, 0.1, 0.9, so 0.009. Here, the first and the third have it, but the middle one's healthy. So same 0.009. Here, only the first has it, and then they have two healthy kiddos. So 0.1, 0.9, 0.9, 0.081. I don't really know why I'm putting those equals, but sometimes I am, sometimes I'm not. I try to be consistent. Okay, here the first one's healthy, and then the last two have the disease, so 0.009 again. Okay, and then this one, they're healthy, diseased, healthy. So 0.081. And then healthy, healthy has the disease, 0.081. And then there is a chance that they're all three healthy. So 0.9, 0.9, 0.9, 0.729. I'm going to add this up just as a check, plus 0.081. Yep, and I got 1. Okay. So, at least one child has the disease. At least one. Which means we're talking about this one, this one, this one, this one, this one, this one, and this one. Right? The only time that at least one child doesn't have the disease is if they're all healthy. So these are the ones I need to add up. So if I add those up, and think about this, an easy way to do it is just to say 1 minus this one, right? Instead of having to go back and punch all that in the calculator. 1 minus this. Remember our formula for our complements? Okay, if I do that, I get 0.271. If they want you to leave it as a percent, since they gave us the initial probability as a percent, right, then 27.1%. That at least one child will have the disease. Okay. The combinations on the lockers at the high school consist of 3 numbers, each ranging from 0 to 29. If a combination is chosen at random, what is the probability of the event that the first 2 numbers are each multiples of 9 and the third number is a multiple of 4? Okay, this doesn't list any restrictions. They don't say anything about numbers can't be repeated. So the key to figuring these out, just like that other one we mentioned with the baby, is realizing, oh, if I've got a 3 number combination and I'm trying to figure out the probability, that's the probability that the first number is something and the second number is and the third number is. So I'm doing the probability that I get a multiple of 9, and then I get a multiple of 9 again, and then I get a multiple of 4. Okay, they're independent events. One number doesn't affect the other number. It doesn't say anything about it up here, that they can't duplicate, right? So we assume they're independent. So I'm just figuring out 3 individual probabilities. Now, My multiples of 9. Now, each number ranges from 0 to 29, so I know my denominator is 30, right? Not 29, because 0. 1 to 29 is 29 numbers. We have the 0, so there's my denominator of 30. So let's see what my multiples of 9 are. Don't forget 0, right? 0 times 9 is 0. That's a multiple of 9. So 0, 9, 18, 21, 27, and that's all. Let's do multiples of 4. 0, 4, 8, 12, 16. Oh, I started to say 18. That's not a multiple. 4, 16, 20, 24, 28, and then that's all. We'll pass 29. Okay, so out of 30, because they're all independent, my denominator is going to be 30 on each one. So 1, 2, 3, 4, 5 out of 30 chance that this thing, that my first number, is going to be a multiple of 9. And because they could both be the same number, there's still a 5 out of 30 chance that the second one's a multiple of 9. And then 1, 2, 3, 4, 5, 6, 7, 8 out of 30 chance that it's a multiple of 4. So what's that? 1 6 times 1 6 times 4 15ths. So that's 4 out of 540. What did I not? Oh, the 4 and the 6 would simplify again. Out of 504. So let's do that. Let's not say that. And your calculator will simplify these for you, remember? But it's good to know some math to make our problems easy. Okay, so final answer. No, not a final answer, because look, I have another 2 that'll cancel right here out of this 6. Excuse me. So final answer, 1 out of whatever 9 times 15 is, 135. 1 out of 135. Okay, that looks like the end of it. Let me know if you have any questions. And have fun, right? Have fun.